Hey guys, what's up? It's your boy K Pinoy, and today we're gonna learn the chapter moving charges and magnetism. Okay, chill. I'll teach you, man. So we know there are two type of charges. One charges is like the lazy one who just simply sits like this 24/7, and those charges, we say those charges, they don't move. They just simply stand like that. And those charges are what we call electrostatic electrostatic charges. Okay, so they're in stationary, they're electrostatic. So let's use the term stationary charges, so that's more better. So those stationary charges, they don't move, and they just simply stay there, and the effect they give out is an electrical field. A stationary charges produces electrical field around it. Remember, a stationary charge, a motionless charge, produces electrical field, and that is what we will learn in the chapter electric current and electric field. You know that electrical field is given by 1 pi 4 pi epsilon sum of the two charges divided by the distance between the two charges. Square them, okay? The square of the distance between the two charges, inverse square, no? But now we are dealing with charges in motion. They will be running like that. Okay, so those are charges in motion. Is it focused? Are you guys focused? Stay focused. Be the 1%. Okay, so charges in motion, they don't produce electrical field, but what they produce is magnetic field. Welcome to physics. So we'll be dealing with two chapters of moving charges, and this chapter's name is moving charges and magnetism, which we'll be learning about moving charges in a current carrying element. And in the next oh, that's a good thunder. It's actually thundering right now. Okay, never mind, I got distracted. And the next chapter we'll be dealing is moving charges. It's moving charges obviously, but magnetism. So here we're dealing with current carrying element, or there we're dealing with magnetism. These two are related with moving charges. So what is the basic definition of electrical? Oh, sorry, electrical. Don't talk about electrical. We're dealing with magnetic. So what's the basic definition of magnetic field? So always remember, magnetic field is represented by a B. I don't know what your school teaches, but my school teaches this. And the basic definition of magnetic field, it is a space. Okay, it is a space around a magnet. I say there will be two parts. One is the magnet, and one is the current carrying element. There will be two parts we're dealing with, but in this chapter we are focusing on current carrying element. So what is a magnetic field? It is a space around the magnet or a current carrying element where the magnetic force is experienced. Get it? I'll just repeat that once more. It's a space around the magnet or a current carrying wire element, I can say, where the magnetic force produced by that can be experienced. And the basic unit of a magnetic field, which I represented by P, is Tesla. I love that car. Okay. But it's electric, man. Come on. Tesla is electric, but we're dealing with magnetism, moving charges. Okay, so first rule we're going to study in this chapter, it's a very simple rule. It's called Biot Savart. What's his spelling? Biot-Savart rule. Okay. So what it states that you got a point P. I want to find it's a current carrying element. I'm going to take this as dl, and this will be the distance between the current carrying element and the point P. I want to find the magnetic force experienced by point P. How do I find it, you ask me? I will use Biot-Savart's law. So according to Biot-Savart's law, it states that, one second. Yeah, the magnetic field produced by whom, man? We're dealing with the chapter current carrying element. I said it before, magnet and current carrying element. We're dealing with current carrying element and the magnetic field produced by this current carrying element. How the magnetic field is produced? Because the current in it is moving. How the current in it is moving? Because the flow of electrons, because the flow of charges. And that is why we say those charges are in motion. And because the charge is in motion, it produces a magnetic field on the point P. And I want to find the magnetic field on point P. So what do? I use Biot-Savart's law. And what does Biot-Savart's law says? The magnetic field produced illa no, I can't. So what does this say? This says that the magnetic field produced by the current carrying element is directly proportional. I'm going to produce that. I'm going to write that as dV is directly proportional to the current flowing through the element. Okay, it's directly proportional to the current passing through the conductor or element. It is also directly proportional to the length of the current carrying element, which I'll denote by dl. Third, it is directly proportional to the sine. Is directly proportional to the sine. Is directly proportional to the sine of the angle between this guy and this guy. So it is directly proportional to the sine of angle between DL and DR. Okay, it's the angle between DL and DR, which are denoted by theta. And obviously inverse square law. And what does inverse square law says? Yeah, you know it. It's directly proportional to R square, where R is the distance between current carrying element and point P. Okay, that's understood. You guys understood that, right? Good. Okay, I'm dropping it, and we're gonna conclude this. Okay, so I'll just write it up. From all 1, 2, 3, 4, we can say that dB is directly proportional to I dl sine theta by R square. I'm going to replace that proportionality sign with a constant k. So it will become dB is equals to k I dl sine theta by R square. What is k, you ask me? K is mu 0 by 4 pi, which has a constant value, which is 10 raised to minus 7. Don't forget that value, okay? It's 10 raised to minus 7. Okay? 10 raised to minus 7. And what is mu 0? Mu 0 is nothing but it is basically the permeability of free space. Yeah, permeability of free space. And if I want to find the total magnetic field, I just use calculus and I integrate it, and I will get the total magnetic field. Now I want to represent the Biot-Savart's law in vector form. So what is Biot-Savart's law? We learned Biot-Savart's law, directly proportional to the current carrying element, the current carrying element, the sine of the angle between DL and R and R square. Now we're going to use cross product here, but I don't want to use that with I, because you know I and DL multiplies, and you know cross product like R cross P is equal to RP sine theta. So if I go like R cross DL become it's I DL sine theta, will become I cross DL. I don't want that. So what I'm going to do is very important, vector form. I'm representing Biot-Savart's law in vector form. Very important in electrical field. This it's almost similar to electrical field. We're just doing some small changes, and here we're going to multiply with r by r. When we multiply by r, we get I dl r sine theta by r cube. Now I'm going to make these two cross product, dl r sine theta, and always remember cross product is anti-commutator. Cross products are anti-commutator. That means if I write r cross dl, the examiner can just cut my paper like that. So always remember cross product is anti-commutator. So you're going to write it dl cross r. Just remember that I multiply by r, so obviously r is going to come here. He's going to be the last one coming because these people were already there. So obviously it will become dl cross r. So this will be our first representation of Biot-Savart's law in vector form. dl cross r, and that will become r cube, not r square. Representation of Biot-Savart's law. First way, you can do this two ways, and I'm seeing you the first way. Is that clear for you? Get it? Should I zoom in, guys? No, I think that's good, right? Okay. So I'm pretty sure you guys understood what I said. And the second way, which is my least favorite, but you gotta learn both, right? You want to learn both. The second way is basically what I'm going to do is that I'm going to give the direction of r cap. Yeah, I'm going to give the direction. It's basically same, but then I don't know. So we all know dB is equals to mu 0 by 4 pi I dl sine theta. But this time they're giving the direction. You know the direction dB is directly perpendicular to. I'll tell you that. By r square, and just because this thing r cap is there, dB will become. I can't keep writing that same thing. Mu 0 by 4 pi I dl into r cap by r square. Last time it was I dl into vector dl into vector r divided by r cube. This time it's I dl vector dl into r cap divided by r square. Vector formation. And you guys know, I'll tell you one thing. If r vector, if this one is like the cross product of this both, then I can say, very important, okay? Very important. Then I can say r is directly proportional to A and r is directly proportional to B. So from this, I have to come to a conclusion that dB, this is obviously dB, right? dB is directly proportional. Not directly proportional, it is perpendicular. dB is perpendicular to dl, that is the magnetic field produced by the current carrying element is perpendicular to the length of the current carrying element, and it's also perpendicular to the distance between the current carrying element and the point P. And this, guys, that means the magnetic field direction I can give by right hand thumb rule. Okay, right hand thumb rule. You know what is right hand thumb rule. Take your right hand thumb rule. This will give you the magnetic field, this will give you direction of current, and this will it's going to give you something. This is direction of current. This one, Guys, it's just it's like 10th grade topic. You guys know right hand thumb rule. Okay. We got some special cases. Let me ask you a question. What is sine 0? It is 0, right? So when theta becomes 0, can I say that dB is equals to 0? That is dB, magnetic field, becomes the least when theta becomes 0. And what is sine? What is maximum value of sine? Obviously it's 1. And where does it get 1? When theta becomes 90 degree. So I can say magnetic field is maximum when theta is at 90 degree, and it will be I dl by r squared is 1. This will be the maximum value. Okay, that's a basic thing. Now we know there are a lot of electrostatic. We were dealing with Coulomb's law, but in motion we're dealing with Biot-Savart's law, and I'm going to just say some similarities between them. So the main important similarity you guys have to realize is that they both follow inverse square law. That means 1 by r square. Inverse square law means both fields are inversely proportional to the square of distance. Square of distance from source, okay? And let me just represent Coulomb's law over here. This is permeability of species. Okay, both follow inverse square law, and both depend upon the nature of medium, and both are long range fields. That means the magnetic field, I have a current carrying element, the magnetic field experience over here will be something. But if I put that somewhere around like Dubai or like Miami, I'm not going to experience anything, right? So both are long range field. That means they become zero long range field. They become 0 when r is equals to Miami, r is equals to Bali. No, when r is equals to infinity, yeah, because they're so far away. And both obey law of superposition. You know what is law of superposition? My English broken. I don't know why. Law of superposition. So what is law of superposition? We learn electrical field. Law of superposition is the sum of all the charges, sum of all the individual electrical field experienced by this. So it's just sum. Superposition is sum. And you sum all of them and you get the total one. And what is the difference? The difference is that magnetic field is a vector source, while Coulomb's law over here is a scalar source. And it depends upon sign, but there is no angle dependency over there. And direction of the electric field is along the line joining the two sources, but magnetic field is perpendicular to the line joining the current carrying element at the point P, and that perpendicular to the length of the current carrying element. Okay, that's all. Now we all know the SI unit of Biot-Savart's law. SI unit of magnetic field is Tesla, and if you tell me definition of 1 Tesla, it is basically 10 raised to 7 times. 10 raised to 7 times the magnetic field produced by a current carrying element of 1 meter carrying current of 1 ampere at a distance of 1 meter from it and perpendicular. Now I want to find. Now we're going to do applications. Very important. Please listen carefully. I'm straining this much to explain you guys. I could have been sleeping right now, but I'm not doing that. And it's like 10 o'clock, and I have chemistry to study, I have English to study, and I got law to study. I know I'm not going to do that, because I'm gonna fall asleep, but still I am using all my time and all my level best to educate and enlighten you guys. So please focus. I know your guys uh, what's that called? Attention span is just effed up. So just focus and try to focus. First application of magnetic field. So we're gonna find the magnetic field around. We're gonna find the magnetic field around. Magnetic field. Oh, we're gonna find the magnetic field at the center of a circular loop. MF of a circular loop. MF at the center. Okay, two applications in there. First application is that we're gonna find the magnetic field MF at the center of a circular loop, and then there the baki, that means a part of it. We're gonna find the MF at the center of a semicircular loop, and then second application is we're gonna find the magnetic field of we're gonna find the magnetic field at the axis of a circular loop. Okay. At that time, we will consider circles as 3D. But right now, it's just 2D. Point O. R is the distance. I consider this AB. Current is going. Current is running. So, what is Biot-Savart's law? Okay. So what is R? R over here is R, right? R over here is R. But what is theta? What is theta? What is theta? Theta is the angle between the current carrying element dl and the distance between the current carrying element and O, that is R. And as you can see, this one is acting as a tangent. And you know what is the angle between the tangent and the circle? Yeah, it's going to be 90 degrees. So that's going to be 90 degrees. And you know 90 degrees is 1. So, you know 90 degrees 1. So it's going to be dB is equals to I dl by r square. Okay. Now we want to find the total magnetic field. To find the total magnetic field, I said you before, we have to integrate it. So we are going to integrate him. I am integrating I dl by r square. What is the constant? When I integrate, when I use calculus integration, I need to take the constant out. I is constant, I can't change I. R is also a constant, I can't change r square. But dl, come on, what is dl? dl of a circular loop will obviously become the circumference of the circular loop. Am I right or wrong? This circumference will become dl. Obviously, it's a length. The length of the circle is going to be the circumference of the circle. So I'm going to take the constant out, which is I and r square. I can't change those, but I can change the circumference if I want to. And as I said you before, this will become 2 pi. What is the circumference of a circle? The circumference of a circle is 2 pi r. Someone has broke something. That's all I know. So I'm going to substitute the value. Pishku. Am I missing something, guys? Yeah, I am. Where the hell did mu 0 by 4 pi when? I forgot about that, guys. Mu 0 by 4 pi is also there. Don't forget about that. Oh my god, I just forgot about that. Pi cancel. So the magnetic field at the center of a circular loop is this one. So this is the MF at the center of a circular loop, and as you know, the circle we consider only one turn, and if it had n number of turns, then I'm just going to multiply it by n in the numerator. Okay, don't get confused. Okay, if there is like 4 number of turns, I'm going to multiply it by 4. And what if you ask me what is the MF at the center of a circular loop? No, if you ask me what is the MF at the center of a semicircle loop, I just divide this by half. And when I divide it by half, I get mu 0I by 4r. One is 2r, one is half r, and this is going to become for a semicircle, right? Semicircle. Okay, good. Now we know when we were learning Biot-Savart's law, after vector expression of Biot-Savart's law, we know that we found the direction of the magnetic field by using right and thumb rule. But how do you find the direction of in a circular loop? How do you find the direction, bro? How do you find the direction? You can't use right and thumb rule in circular loop. You're gonna use clock rule. Hello, excuse me. What is distracting you? What is stopping you from quitting your dreams? What is making you give up? Remember, you are built different. And focus. I'm going to use another beautiful rule called clock's rule. I'm going to use clock's rule to find the direction of magnetic field in a circular loop. That is, if it goes clockwise, then it is south. And if it goes anti-clockwise, but I know, then it is north. Anti-clockwise north and southwise is clock. And clock means the current, if it's clockwise, that means at the south pole the magnetic field goes into the south pole. The magnetic field enters into south pole. How do you draw a bar magnet? Obviously, this is going from north to south. It's going over here, right? So everything is getting inside, right? So from a magnetic field is passing from south to north. It's getting into magnetic field getting into the south, and from north it is getting out of. So I'm going to denote a dot. That's all. It's clock rule. Now we're going to learn about a magnetic field at the axis. Okay, we're going to learn that later. Magnetic field. I'll just give you a brief introduction. We're going to learn later. We'll learn about magnetic field at the axis of a circular loop, and in this we will be considering a thing as 3D. That is, if I give you an example, the circle is going to be like this. This is going to be a circle. See, this is going to be a circle. And at the axis means this will be the axis. When we circles at z-axis, and the axis is going to become x-axis. So I'm going to find the current carrying element in the x-axis. Circle is at z-axis and find current carrying element at z-axis. So consider this has to be the circle. So this will be the point P. Okay? This is a circle. This will be a point P. Let this be the circle, okay? And the point P is over there. And what is R? You're going to say R is the distance between the current carrying element and the point P. So I'm going to consider the current carrying element over here, dl, and this will become R. Right? R. Let's give this x, and let's give this radius as R. Okay, radius is R. And what is the angle between this and R? What is the angle between dl and R? One goes like this and point P is over here. Right? 1 second. Yeah, what is the angle between the current carrying element and this thing? It's going to be 90 degrees. It's always going to be 90 degrees. That means this thing is like this. And point P is over here. It's going to be 90 degrees. It's going to be 90 degrees. Yeah, I'm going to tell her tomorrow. I'm pretty tired. I need to now. I'll tell that later on. How you're going to find the magnetic field at the axis of a circular loop. So till then, what do you guys study now? Study that properly, and I'll see you later. Bye bye.